All right, so hopefully this is working. I'm not sure if the stream is live, but okay, yeah, it seems to be working. So, hey everyone, today we're going to be talking about embedded security. I'm going to be hopefully giving some background information on embedded systems, threat modeling, secure boot chains, and just overall all the things you might need to know for the talk next week, which I will also be giving on console hacking. I'm hoping to do that on the Nintendo Switch and kind of talk about some of the work that I was involved with in that and all of that fun and interesting exploitation stuff. But for this week, we're going to need to cover a lot of the background info before we can get into that. So, yeah, we need to understand things before we can break them. So, what is an embedded system? So, your embedded system is basically anything that is going to be using a microcontroller in place of what would traditionally have a dedicated circuit. So, a microcontroller based embedded system is differentiated from your traditional general purpose computers by their scale and their use. So you typically have a lot less resources on an embedded system, and almost always you're using them for a very specific task rather than just in general using them for arbitrary computation like you would on a desktop computer. So many traditional circuits have indeed been replaced by embedded microcontrollers historically. On the left, we have an example of an embedded Ethernet controller, and on the right is an entire embedded system inside a voting machine. So the thing about these systems is that they are not the primary interaction point for the machine, and they don't do the primary computation for the machine, especially in the case of the Ethernet controller. But they do run their own entire real-time operating systems, and they are Turing complete machines. They're just embedded within a larger system. So why do we care? There's a surprising number of embedded systems out there in the world, and when we think, well, what immediately comes to mind? We have, say, routers, modems, your smartwatch, your IoT toaster, whatever, and those we conceptually think of as using and requiring it like an OS and something that runs applications and all of this sort of things. But it includes a lot more than that, and a lot of surprising things out there will run embedded systems. So like your mouse or your monitor or your calculator, they almost all certainly have moved out of dedicated circuits and into running some kind of RTOS with an OS. Your microwave, your dishwasher, your thermostat. Surprisingly many critical systems run embedded OSs these days. So like your car brakes for anti-lock braking systems are actually running a real-time operating system. They have firmware. They can get updates. In the case of modern cars like your Teslas or whatever, they actually get over-the-air updates sometimes, and that might be something interesting to consider. You also have modern fly-by-wire avionics controls, medical equipment, all sorts of things, and they all have the same intrinsic design constraints. So when we're talking about embedded systems and the security of embedded systems, we're not just talking about the security of your IoT toaster, we're talking about the security of things that matter. And here's a tweet I really like. Software update failed, this is my dishwasher. And I have this captioned as more functionality, always a good thing, because when we add embedded systems, we gain a lot of flexibility over dedicated circuits, but we also introduce a lot of complexity. And complexity can be good, or in the case of your dishwasher doesn't work because the software update failed, not good. One second.
Issues with OBS?
Okay, that should be
Yeah, it
better.
would be the first time.
All right. Can people hear me? Does this work? Okay, cool.
Yeah, we can hear you.
So, when we're considering embedded devices, we really, in these kinds of critical systems, we want to know, how do we trust these devices? Because when they were running dedicated circuits before we started replacing them with embedded systems, we knew that at a fundamental level, what they could do was constrained by the design of the circuit, because you can't have a car braking system that does anything other than apply the brakes if the circuit only has one possibility, and it can never change. But when we replace it with an embedded system, well, the constraints are imposed by the firmware that the system is running, which does provide a lot of flexibility, but that also introduces avenues for exploitation, just because now your system is capable of arbitrary computation, and you need to not trust you can't just trust the circuit, you have to trust the firmware. So one of the big ideas that we're going to be talking about is, well, where does this firmware come from? How is it stored? And how is it executed? So the answer to the first question, which is where does your firmware come from, is going to be a little bit of a hardware question. So the firmware is going to be stored on, almost always, on some kind of non-volatile flash memory on external to the actual chip doing the computation. And flash is used in basically all systems to store various types of data, your config files, file systems, firmware, OS images, basically anything that is required to preserve contents over reboots. And in the case of firmware, we want to be able to have writable non-volatile memory, because often these types of systems want to be able to apply firmware updates. If you didn't want to update the system ever, you would almost certainly not use an embedded system. You would use a dedicated circuit, because you don't need that flexibility. Your flash will be communicating with the microcontroller for your embedded system over some kind of standardized protocol. We use basically 99% of flash chips will use either SPI or I2C buses. But these are standardized. Is there a question? Okay.
I think you were getting a little bit of echo.
Yeah, that was Abby's mic echoing. I just muted it. Okay, so your SPI and I2C are going to be communicating with all types or are being used to communicate with all types of different peripherals on your board, like sensors and various like controllers. You have like display controllers, various random peripherals. But in our specific case, we're thinking about flash chips, because this is where the actual executable code for our firmware is coming from. And the thing about standardized protocols is that, well, it's not just the microcontroller that's going to be talking to these things. It's going to be also like anything capable of speaking the protocols. So in this image, we have a PCIe, or I think this is regular PCI Ethernet controller, and it has a firmware like flash chip on it that contains some kind of firmware, and we just soldered to some test pads, and you can read and write to the flash and overwrite it and replace the contents. So the flash itself can't be considered like an authenticated or remarkably trustworthy source for the firmware all on its own. So that gets into the next question. Well, how is this firmware executed? If it's on a separate chip, what is happening when you boot up your embedded device? So basically, your microcontroller is going to be, when you enter reset, which means you are powering on the device, you're applying power, the microcontroller is going to be executing what we call the boot ROM. And the boot ROM is a read-only memory ROM, which is going to be masked in at the factory. Almost always we use mask ROMs for this. And that's basically just a term from photolithography. It's just how the chip is manufactured. But the important part is essentially that your boot ROM is actually in your SoC, your system on a chip. So your microcontroller itself has this code, which is essentially burned into it. It can never, ever be updated outside of the factory. It would be essentially impossible. So it will always execute this code when it turns on. And since this code is read-only, we have some considerations. So if we want high flexibility on our devices, we would want as small of a boot ROM as possible, because since this code can never be updated, we want it to be doing as little as possible before getting into code that can be updated, in case there's bugs, in case there's whatever. So typically we call the boot ROM the first phase of the boot chain, in which you have a series of different software components that will be increasing in complexity. So this image is a DSLR microscope image of the MSP 430 boot ROM by Travis Goodspeed, and it's really interesting because the thing about mask ROMs is that you can actually, with a microscope powerful enough, after maybe decapping the chip, you can actually see optically the gates that are making up the boot ROM, and seeing if you were very dedicated and had a high enough resolution image, you could reconstruct the code that is being executed just by looking at the image. And I think that's really cool. So your boot chain is going to be transferring execution between different stages. And this is the fundamental idea that almost all machines of any kind that are used in the modern day are going to be subject to, because we typically, as I said, want to minimize the amount of complexity at the very first stage. So we're always going to want to be increasing complexity as we move into more and more easily updated systems. So you will typically, in a modern PC, have many stages of your boot chain. So your boot ROM is actually, on modern Intel machines, going to be in the CSME, the Converged Security and Management Engine. And that's actually the first separate processor that begins execution, and it will initialize the main processor. But simpler systems, like our embedded examples of microcontrollers, will have many fewer stages, or sometimes only 2 stages, boot ROM and then firmware. But the most critical takeaway from this is that the only constraints which you can possibly guarantee are imposed on the system are those imposed by the boot ROM. So when we're thinking about critical embedded systems that are running your car brakes, well, you can no longer have a circuit that you're 100% sure will always apply the brakes. You can only have a boot ROM that you're 100% sure will impose some kind of restriction on the next stage of firmware that is being loaded. And this is a really important concept to understand, because when we're gaining all this flexibility from using embedded systems, misunderstanding the way in which constraints are imposed on your system and the way in which arbitrary computation is limited will determine whether or not your embedded system is safe and useful and reliable, or if your embedded system is going to turn off your car brakes when you need them. So this gets us into the idea of threat modeling. And threat modeling is essentially the abstract model of possible attack vectors and appropriate countermeasures. So we're thinking about a specific system, and then we are thinking, where are the possible attacks going to come from, and what are possible countermeasures we can deploy to prevent those attacks? And this is, in short, the question, what kind of security makes sense for a potential target? But it's more complicated than that, because it depends a lot on the actual considerations of like the way the device will be used more than the device itself. So how critical is your device? What's the attack surface? What do attackers have to gain from compromising your device? And most importantly, how do we constrain the operation of the device? So when we're wondering where an attack might come from, well, the requirements for security vary wildly. If you have an embedded device which is only ever used in a situation where it is physically guarded or in your house or in some kind of scenario where you trust the physical location of it, well, then you don't need to worry about physical tampering, and your attack surface shrinks considerably to only remote attacks. But there is the opposite case in which there's something like your phone, which might store a lot of personal data about you and be taken outside of your house, outside of your controlled environment. And then you need that system to function with some degree of assurance in terms of security, even under the assumption of a malicious physical attacker. So our main threats to embedded systems are either this physical tampering or remote exploits which will replace the firmware, or both. And the key convergence point of these two things is the idea that we want to prevent the modification of the flash contents, because in the case of physical tampering, if we're concerned about a physical attack and the attacker can just swap out the firmware on the flash chip like we showed in that other picture, well then we have immediately failed. And if we are concerned about remote attacks, well, we are also concerned about persistent remote attacks that will, after landing one exploit, permanently compromise the system. So in most scenarios with most devices, our threat model is likely to include the replacement of flash contents, but if we are not concerned about that, then we don't need to worry about secure boot chains. And this is why threat modeling is important, because we don't always need to apply the same guidelines to every device. And so, yeah, here's some examples. So like your router, right, is going to sit in your house. It has user data, but it's mostly low risk of hardware attacks because you're not really concerned about random people walking into your house and then disassembling your router and flashing new firmware to it, because at that point most routers already have a button on them that resets the password or whatever, and it's just not your primary concern at that point in time. But it is an internet-facing device, so we are concerned about remote attacks, and that means we're still concerned about secure boot chains, just because we don't want remote exploits to have permanent control over the router. We want, on a reboot or on a firmware update, any possible exploits can get fixed. But on a game console, for example, this is a completely different scenario, because not only are we worried about internet-facing compromises because these devices do have internet access, we are also worried about the chance of hardware attacks, because in the case of a in the abstract sense, because in the case of a manufacturer, the manufacturer cares very much about hardware attacks because they want to enforce DRM on the user. They want to make sure that the intellectual property of their games is protected, so they will go through very much effort to not only secure the device from arbitrary external compromise, but also compromise of the person, or compromise by the person who purchased the device, which is a completely different threat model. But the idea overall is, how do we ensure that the firmware running on the device is the one we expect? And this gets us into the idea of the secure boot chain. So we have talked about the idea of the boot chain, in which the boot ROM is only doing a very small part of the initialization of the system, and then it's going to get into more and more complicated stages that each increase complexity, build abstractions on top of one another, and overall initialize more hardware. But that means that we actually need to be verifying each stage as we load it and before we start executing that stage. And that's the idea of the secure boot chain. So naturally, we have the question of, well, if it's a chain and each link in the chain verifies the next link, well, what's the first link? And that's what we call the root of trust. And the root of trust for almost all modern devices is going to be the boot ROM, because we have to eventually trust some component. We can't just arbitrarily require more and more systems and then think that this will eventually lead to some kind of perfect idea of security where we have the secure system and don't need to rely on anything. It's just not possible. So we need to eventually trust something. And the boot ROM makes a lot of sense for this because it can't be modified. It must always exhibit the same exact behavior. The state machine will never change. And we know that it exhibits the intended manufacturer behavior. So in the eyes of a manufacturer who's creating a device that they want to be secure, this is essentially the only idea that makes any sense. So some examples of roots of trust are, one I mentioned before is the Intel CSME, which is going to be on all your x86 Intel laptops basically produced in the last 10 years. The AMD platform security processor is the same idea, but for AMD. Most Android phones or anything that runs Android in a secure, or most embedded devices that are of note will be running ARM chips that use Trust Zone. So that would be your phone, the game consoles like your Switch or anything like that. And then other devices that are especially high value targets will have roots of trust that are actually rooted external to the system on a chip, like the Apple T2 or Samsung's Knox systems, where your root of trust is actually yet another separate processor than the trust zone, and the trust zone is just a later link in the chain. So we have our root of trust. So we have the first link in our chain. We are inherently trusting this read-only memory to always impose some kind of constraint on the system. And what is the constraint that we want to impose? Well, at every link in the chain, we want to validate that the next link has integrity, in that the link is not corrupted, and authenticity, in that we can validate the origin of that link. Typically, we want the next link in the chain that is being initialized, or that will be executed to initialize the system, comes from the manufacturer, and integrity, we want this thing not to be corrupted. So the simplest form of validation we can provide is a checksum, which will provide integrity but not authentication. And a lot of embedded devices don't do proper threat modeling, so they will use checksums when they really wanted something that provided authentication. So for us, this is a good thing because a lot of these devices we want to run our code on, but for the manufacturer, this is very much a problem. As the old adage goes, the S in IoT stands for security. So when we think about checksums, they're very fast, but they're, We will still talk about checksums with the understanding that just a checksum isn't going to be sufficient, because they are the foundation for the next thing we're going to talk about. So CRC is basically the only checksum anyone uses. This is your cyclic redundancy check. CRC32 is very, very popular. It is a checksumming algorithm. It is extremely fast to execute and compute a checksum, but it is not a hashing algorithm. It will protect you only against accidental corruption of the data. It is very, very easy to produce an arbitrary chunk of data that will provide a given CRC and pass the checksumming check if you are doing it maliciously. MD5 is a cryptographic hashing algorithm, so it's much more secure than just a checksum algorithm. It was designed by Ronald Rivest, and it actually attempts to prevent collisions. So unlike CRC32, the idea is that you can trust the hashing algorithm in that if you have a hash and you have something that that when you run the algorithm against that data, it produces the hash, you can be reasonably confident that this is the only data which produces that hash, in that it tries to prevent collisions. But unfortunately, MD5 is considered cryptographically broken in that it is possible to compute pre-image attacks on it, and while they're still kind of emerging and it's not super common to see MD5 collisions yet, they've been done, and MD5 is now considered unsuitable for further use. So the hashing algorithm everyone would recommend to you is going to be SHA, which is the secure hashing algorithm, SHA-2 specifically, which was designed by the NSA. And it is considered on modern hardware collision resistant in that it would be computationally infeasible to arbitrarily compute a piece of data that will conform to a checksum given the checksum. And a pre-image attack is one in which you will have the data that you want to conform to the checksum, which is the kind of attack we are interested in as an attacker. Because if we can replace the firmware with random bytes that will still pass a checksum, well, that's not too helpful. But if we can replace it with our own malicious code, that is helpful. Currently, SHA-2 is considered collision resistant for both of these types of attacks on modern hardware, but we will see how that changes in the future. So we are now going to get into signatures. So in normal asymmetric cryptography, we've talked about this in past lectures, but as a very brief primer, you have a public encryption key and a private decryption key. And the idea is that anyone can encrypt messages that only the private key holder will be able to decrypt into plain text. And we've talked about a lot of different very, very detailed ideas related to these signatures, their security properties, and various things. But what's really, really interesting is the opposite, which is where the decryption key is public and the encryption key is private. And this gives us a unique property in comparison where the private key holder is the only one who can produce valid encrypted ciphertexts. And then anyone can decrypt those ciphertexts to know that the private key holder was in fact the one that created the data. And this is going to be the fundamental idea behind our ability to implement secure boot systems. So the problem with asymmetric crypto is that it's very slow, and we might, as a naive approach, try to encrypt the entire firmware with the signature scheme that we just devised, where the public key can decrypt the data and the private key can encrypt the data, and then theoretically only the manufacturer could have possibly encrypted that firmware, so we know the firmware is correct. But this would be incredibly slow, and as we talked about with our embedded systems, we are often constrained on resources. So instead, we're going to use those checksumming algorithms that we discussed before, and we're going to be encrypting the checksum. So an encrypted checksum is give or take a signature. There's some other data usually embedded. You have like a structure that contains the checksum, and there's a lot of metadata, and you need to parse that structure. ASN1 is the really common one for this. And something to note from an attacker perspective is when we look at like different devices that we might want to exploit that are using these kinds of systems for secure boot, we might notice that the parsers for these signatures are very complex. ASN1 is an extremely complex domain-specific language, so they will often have bugs in them, especially if the people manufacturing the device have written their own parser. And that's just an aside that we might want to think about. So for checksums, we don't really care about collisions because in CRC, you're only trying to validate that the data has not accidentally changed due to bit flips. Maybe the hardware is unreliable or radiation has caused the flash to decay or degrade in some capacity. But in signatures, we are not using checksums. We need cryptographically secure hashing functions. And now collisions are very, very important because if you have a hash collision, say in MD5, and your signature that you have used uses MD5, well, now an attacker can craft they say your signature parsing is correct and your signature encryption scheme is perfectly secure, but if your hashing algorithm is wrong and has a flaw in it, well, then an attacker can just arbitrarily compute a new firmware which will still match the hash, and now it doesn't matter, your security is broken and your secure boot is compromised, which is why you're going to always as a manufacturer want to use SHA-2 over MD5 because SHA-2 is currently considered collision resistant. But in the future, this might need to be reevaluated as SHA-2 might not always stay collision resistant. New weaknesses can be found, computing power will increase, etc., etc. So the types of asymmetric crypto you can use for signatures, well, we've got two very, very popular ones. And the first one is RSA, which is Rivest Shamir Edelman, and that is the Rivest from MD5 that we discussed earlier, along with many, many other things. All of the people in the R, S, and A in RSA have made a lot of very important contributions to both like cryptography in general and the security we're concerned with. But RSA is the most popular asymmetric crypto algorithm. It was also the first widely used one, first public one, I believe. And it is unfortunately very fragile, so your signature structure is actually very important. You need padding, and there's a lot of requirements that we have talked about in previous lectures that we might want to review if you don't remember these things. But the TLDR is that we consider these secure but easy to mess up. And that's just due to how fragile the algorithm is and the signature structure that you're going to need with all the padding and such. And then the other one is elliptic curve cryptography, which is the up-and-coming alternative. It's been pretty popular the past, let's say, decade or so. It's been gaining popularity. It's going to offer the same protection as RSA, but with smaller keys and doesn't require padding. It still can be fragile because the curves are very important. Depending on the curve that you select for your signature scheme, you can either have a very strong cryptographic properties or very useless cryptographic properties. And for an example of that, you might recall our talk on curveball, which was the name for the Windows ECC signature bug. So in the idea of signatures, both RSA and ECC are hard to get right. There's many different implementation errors. Errors in either the checksum or the encryption scheme that you're using compromise the boot chain completely. So the crypto is actually important. Who knew? So maybe play more crypto CTF categories, and there are indeed real-world implications for these. And then the quote at the bottom: if we were solving any crypto, we'd be dominating right now. A classic RPI sec quote. So a flaw in your crypto or your hash compromises the secure boot chain. So you're going to want to not roll your own crypto and use good standards for your hashing algorithms. So typically, the recommendation is going to be SHA-2 and ECC for modern applications. ECC is going to be better on your embedded systems, often because of the resource requirements being less, and SHA-2 just because of the collision resistance. So our key takeaways from this talk and the background information we've been going over are going to be that your verification of each new link is not sufficient in and of itself, because a bug at any stage in your boot chain is going to break your chain, and if you implemented a poor verification of either the checksum or the hashing algorithm or your asymmetric crypto, you're basically screwed. So vulnerabilities in the boot realm are going to be the most powerful just because, as we discussed, you can't patch them. They impose the fundamental constraints of the system. If you can't trust the root of trust, your entire security scheme is broken. And unfortunately, many of the devices that we see in the wild only secure some of the links. So even on modern PCs, like if you use Linux especially, a lot of people will enable UEFI secure boot, and that's one of the links in the chain. And those PCs will also use Intels like BootGuard, CSME, root of trust. So the first few links are secure to a reasonable extent, but then you use Grub, and Grub loads unsigned kernels, and now you've broken the secure boot chain, and it doesn't matter anymore. A lot of routers and modems and other consumer devices will use signed firmware validation, and they'll enforce signature checks, but then there's a root shell on UART whenever you boot it up, and now you have broken the last stage in the boot chain, or a buggy web app in that firmware is also breaking the last stage in the boot chain, and it doesn't matter anymore because you've compromised any part of the system. And that's why secure boot chains are especially fragile, is this idea that we need to keep each link constrained into the fundamental constraints imposed by the boot ROM, which is usually that each link is signed and has integrity. So the only way we can have a reasonable assurance of our firmware validity is going to be having a root of trust that you assume has no bugs. So your boot ROM must be very simple. If you can trust it has no bugs, and it will load a firmware, it will validate the signature, and it will execute it only if the signature is valid, then you can consider your root of trust secure, asterisk. And we also need to make sure that each successive link in the chain is secure. And this one's more difficult because as your boot chain increases in length, it's also increasing in complexity, and the code base becomes larger and larger, and you need to audit more and more things. And all of this is in the face of, or only secure in the face of software attacks, because we're not accounting for hardware like power cycle or clock or power or clock cycle glitching, where your hardware might do things that are faulty. Like if your boot ROM root of trust has no bugs in it, well, if I drop the voltage at a specific point in time while it's doing some kind of signature validation, well, maybe the instruction that's supposed to go somewhere else and not continue executing doesn't do that, and all of a sudden your root of trust is now buggy when you didn't have any bugs in it. And these are all considerations that are taken into account when you're designing modern secure embedded devices like your phone or your game console or whatever. There's a lot of resistances that you can build in for these kinds of hardware attacks. So this was a lot of background information. It was pretty dense. I'm hoping it wasn't too overwhelming. Next week is going to be the fun week. I'm going to be applying all these things that we just talked about, all this background knowledge, to console hacking and hopefully the Nintendo Switch. That'll be Friday at 6 p.m. Same YouTube channel stream. We will be sending a link beforehand. Anyone who's at RPI, join the Slack. Stay safe with the whole virus. So anyone have questions?
One question that I have actually is I was wondering how the checksums would work with encryption, because if the checksum is a short value, would that just be brute forceable? In which case, the encryption, the signature, wouldn't really do anything.
Yeah. So the idea of signatures is that your signature is only as powerful as your checksumming/hashing algorithm and your encryption algorithm, and it's like the lowest. You're taking the OR of them, right? So if you use CRC32 as your checksumming algorithm in your signature, and you have ECC, which is implemented perfectly, it doesn't matter because it's trivial to implement an attack that will brute force the CRC and find collisions, and then it doesn't matter that your signature implementation was perfectly valid because you picked poor standards that didn't apply to the threat model.
Okay, that's fair.
Any other questions? I'm just waiting for stream delay. Okay, doesn't seem like it. So yeah, hopefully everyone retained some reasonable amount of that information, and next week we'll be talking about console hacking, which will lean a lot on these concepts. So yeah, everyone have a good weekend.
Yeah, you too. See ya.